Hello, welcome to the Work and Energy and Power videos. We're going to start talking about conservation of energy first, since it's probably the most important principle that we're using most of the time when we're solving questions to do with energy and work and power and all of this. Principle of conservation of energy says that energy cannot be created or destroyed. It can only be transferred or transformed. So you can say that it cannot be created or destroyed, but it can be transferred or transformed. Okay, so that's the principle of conservation of energy. You can write it out in whole words, or you just remember these four and then put it into a sentence if you ever get asked the question. Now, what that means and how we use that in questions, we'll just see more and more as we go on with the videos. But what's important is to also appreciate that there is this thing in physics that they call, it's a bit of a theoretical thing that doesn't really so much exist, but we use it as a model all the time, and it's very useful to solve problems. And it's called a closed system. Closed system. And a closed system is something that doesn't interact with its environment. It's not open to interactions, and information and energy doesn't come in and come out, and it doesn't exchange anything like that. And there's another way of formulating the law of conservation of energy, which is to say that the amount of energy inside of a closed system is basically constant. So amount of energy here, if it's not interacting with the outside, the energy amount in here is a constant. So it can change, it can go from one place to the other and move around the energy and be transferred, or and it can be transformed into other forms of energy, but it cannot sort of disappear or go less in quantity or go more in quantity, increase or decrease, which basically would be like the ideas of creation and destruction here. But it can be transformed and transferred, and this is all inside of a closed system. Okay, but if you have an open system, if this then became an open system and it was connected to another one over here, and then that wasn't true and it's open, then yes, the energy can here increase or decrease depending on the transfers that there are between the two systems, and obviously it can still be transferred and transformed. That always happens, but these two would then well, they wouldn't be created or destroyed, it would just be increasing or decreasing. But within the system it would seem like it's being created or destroyed because it's just increasing. But that's only true for closed systems. Okay, so hopefully that helps and or makes sense, and as I say, we'll be using questions and see how we can use this practically. And you'll see that it's a very easy idea, and it's also very useful, and it can save us loads of time in terms of doing questions, which we'd normally possibly want to do with velocity and acceleration equations, and it could take much longer using those. So an example of a transferal of energy would be the idea of work done, for example. So work done is a really important concept in physics, and we'll use it a lot also, and you'll get to grips with it as we use it more and more. But it is the work done on some system is exactly equal or the same thing as saying the energy transferred. The energy transferred. Okay, so an example of that would be if we transferred, okay, energy transferred. An example of that would be, for example, we have a table like this, and maybe it's made of, it's got ice on the top, so it's got very little friction, and it has a block on top like so, and the block is then pushed by a force F over a certain amount of distance, and the distance is delta S. And if there's no friction, then the block is going to accelerate, and it's going to increase in its velocity until here it's going to have a new velocity. Here perhaps it's at rest, we're going to say that it's at rest, and here it's going to have a velocity v. And what this equation is saying in this case, or the particular example, would be the same as saying that when this force does work on this block over that distance, the work done normally you calculate it as the force times the distance through which that force acts, and they have to be in the same direction. We'll see examples where there's a little bit of a complication and the direction is not quite exactly the same, but there's an easy way of getting around that. But the work done is normally calculated as this: the force times the distance through which it acts, and that would be the same, exactly the same as since we're horizontal here and it's not gaining any height or potential energy, then it only all goes into kinetic energy, which is the same thing as half mv squared. So in other words, if you knew the force and you knew the distance through which it's going to act, then you could say that's going to be exactly equal to half mv squared, and if I know the mass of the thing, then I can calculate v and know at what velocity it goes here. So in other words, all of the work that I do on this block is going to go into kinetic energy, and so that's going to be my energy transferred, and that will be exactly as much as the work done that I put into it. Now if there is friction or anything along those lines, or any energy loss like that, then some of the energy is going to go into the friction and other energy is going to go into the kinetic energy. But it's still the energy is being transferred. It's work done is then going to go into the amount of energy that's lost to friction plus the energy that it goes into kinetic energy here, and so V would be smaller than it would be without friction, obviously, and the rest of the energy would be converted into heat. Maybe if it makes a little bit of a sound, some sound energy also. Hopefully that makes sense about this idea. It's a very important idea to have in mind in physics. The relationship between the work we do and the energy that is being transferred. So in mathematics, our equation would then look like F times delta S, which is the distance through which F acts, is exactly equal to half mv squared, and this would be in the case where we're moving horizontally. We'll do more examples of when it's moving vertically and problems like that as we go on. And now I wanted to, after I've mentioned a little bit about conservation of energy and work done, I want to talk, just make a quick list of different forms of energy that you might have, and a good way of separating them. Forms of energy, separating them in groups. So I'm going to give you several categories of types of energy, and then give you a list of things and of types of energy more specifically, and you can make notes of those, and that will be very useful. So in total I'm going to talk briefly about four types of energy, and the four types are described as mechanical energy. Then you have the energy that is contained in matter, so energy in matter. Then you have electromagnetic energy, EM energy, and finally we can call these probably alternative forms of energy, be a good way of calling them, alternative energy. So mechanical energy. Mechanical energy is normally attributed to things like kinetic energy. So I'm going to underline these. I'll underline them all in yellow so that I don't bore you to death changing colors. Like so. And In mechanical energy you have kinetic energy, you also have gravitational potential energy, you have elastic potential energy, and sound energy. Okay, so hopefully you know a bit about all of those, and we'll know more as we do more practice and we go into the next videos also. Then there is energy in matter, and energy in matter normally includes things like nuclear energy and thermal energy. So this is energy stored in matter, either inside of the nucleus of an atom, or in terms of the movement of the overall average of the movement of the particles, which is really a type of kinetic energy, but we normally call it thermal energy. And then we have chemical energy. Chemical energy is very strongly linked to potential energy. It's got to do with the potential energy inside of the bonds of the chemicals and the atoms, the molecules, and also with the other potentials such as the oxidizing potential and things like that. But about those you've got to ask your physics teacher, chemistry teacher, who will know more about them than I do. Then we have EM energy, electromagnetic energy, which sounds very sophisticated, but it really has to do with things like electric energy, magnetic energy. Then we have radiation energy or electromagnetic spectrum energy. So EM spectrum or radiation energy. So that's the energy carried by photons, for example. Some of them have a lot of energy, like gamma rays and X-rays and things like that. This goes out in radially. And then finally the alternative types of energy, which are all the ones that you read about in the newspapers and things like that. We're trying to make very efficient or as efficient as possible, and we still haven't quite managed as well as we will eventually end up managing, I'm sure. Wind energy is one of them, obviously. Then we have also tidal energy, which is not quite as used as wind energy. And there is geothermal energy. It has to do with the temperature differences as you dig big holes on the earth. And hydroelectric energy. And really hydroelectric energy has a lot to do with the potential energy of the water that is at a certain height as it comes back down. So really a lot of these are related, but normally we distinguish between these types of energy since they appear in different formats also, and it's useful to categorize them like this. Okay, so that's a good enough list for now. And so we've talked a little bit about the idea of work done, and really work done is such an important idea that I'm going to talk quite a bit more about it in the next video. And but hopefully this is a nice introduction and useful to the idea of conservation of energy, what a closed system means, what it is, and how you can express the law of conservation of energy in these two ways. That energy cannot be created or destroyed, but it can be transferred and transformed. I'm not really sure why I wrote the same word here twice. I apologize about that. I should say transformed from one type of energy to another. Transformed. And the second one was that the energy inside of a closed system is constant.